Hi, everybody. I will wait a few more minutes, not a few more minutes, a few more seconds before we start to let people come into the Zoom room. Okay, we're going to go ahead and get started. Welcome, everybody, to the Green Bank Community Zoom. Hope everybody's having a great day. I'm going to start off with just a quick observatory news. We had a successful public eclipse viewing party at the observatory, although it was just a partial eclipse here, shown by the little picture in the middle with the projection. We handed out 500 glasses. So we had quite a few people show up at the observatory, and to the right shows pictures taken with the 20-meter educational radio telescope. Just shows the dimming of the moon and the radio wavelengths at L-band during the eclipse period. We'll be, as a reminder to everybody, we have extended maintenance this summer to work on the wheels as well as the foundation. So we'll be shut down a lot from May 6th to September 26th. So now I'm going to hand it over to Jay Lockman, who will introduce our speaker. Go ahead and take it away, Jay.
Thank you. Thanks, Dave. Thanks very much. Our speaker today is Paul Law from our Chetri Observatory, speaking about magnetic fields in an infrared dark cloud. Let me remind everyone to submit questions through the Q&A button at the bottom of the screen, and we'll take those after this talk. And also, this session is being recorded and will be available for viewing through our website within a day or so. So, Paul, take it away, please.
Thank you very much, Jay, for introducing me. And also, let me start by doing a share screen. And I hope everyone sees the screen clearly.
It looks good, Paul.
Yep. And first, again, thanks so much for the Green Bank Test Group to giving me a chance to share about my research. And also, I'm very excited to share with the community about this work, which is the polarized light from the massive protocluster, which is known as the POLIMAP survey, which is aimed to dissecting the raw magnetic field in a massive infrared dark cloud. So this is actually also related to a lot of people, which is also mentioning here in the bottom of the slide. And I will start by beginning introducing some of the background of this project. So actually, this is very interesting by actually aiming to answering one of the big questions, which is why we want to study massive star and star cluster formations. So one of the key things that is interesting is massive stars are rare, but they play significant roles, especially because of the radiative heating and outflow injects a vast amount of momentum and energy into interstellar medium, which can actually further regulate newer star formations. And also these processes enrich the interstellar medium chemical content and impact the initial chemical conditions of the next generation star formations as well. So this actually tells us already something, which is massive star and star cluster formation is a multi-scale process and very dynamic. So one of the key questions that from this project we really want to learn about is there a simple theoretical model to explain massive star and star cluster formations? So there are two competitive models. One is the co-accretion model, which is essentially a scaled version of low mass star formations, which collapse in a well-defined structure, which is known as the prestellar dense core. And to have this very massive dense core may be supported by turbulence and or magnetic field, which is the key mechanism we're going to discuss in this talk. And the other competitive model, which is more related to the cases that the stars chaotically gain their mass via the global gravitational collapse of the clump without passing through the massive prestellar core phases. And in many of these cases, the massive stars tend to form in a clustered environment. So these actually allow us to really understand. We want to use observation and hope we can learn about more, especially the role of magnetic field, which is the second question we really want to pinpoint of, because we know that gravity, turbulence, magnetic field, and feedback, for example, shocks and outflow, plays key regulating role in the star formations. And of course, in the last decade, magnetic field has been recently suggested to play a really dynamical, important role in regulating initial conditions and even the later stage of star formations. So especially, for example, regulating fragmentations in the molecular cloud and the IRDCs, of course, could be a potential way to support the dense and massive cores. So to characterize the magnetic field properties will allow us to re-understand how the massive star actually forms here. So the observational side here, the main related here is I want to introduce the POLIMAP survey. So the POLIMAP survey is a survey which jointly with the SOFIA-HAWC Plus of 214 microns with the green band telescope Argus, which is with the high resolutions about close to 7 arcsecond. We mapped 6 out of 10 of the IRDC study in Blockland 10 2009 sample. So with the green band telescope, we actually mapped a large area of this cloud with 13C01 and the C18O1 with a high velocity resolutions here. So the goal here with this sample of cloud, we are able to systematically study the magnetic field properties across the mass, size, and different environment as well. So here it just shows some of the images and the field of view of these infrared dark cloud samples. So in particular, I'm focusing on one of the infrared dark clouds, which is known as one of the most massive infrared dark clouds, is G28.37. So we have a mass close to 70,000 solar masses at a distance of 5 kiloparsec. And here we see the more or less the field of view of the GBT-Argus. The cloud is defined by more or less the ellipse, by the green ellipse here from Simon et al. 2006. And the yellow is where we have the SOFIA-HAWC plus coverage. So one of the things we are, of course, interested in the magnetic field, which is related to the inferred from the price, thus emissions. So from here, we showed the on the background color, we have the 214 intensity map. On top of all this vector is the rotated polarization angle, which tells us the magnetic field orientations. So we can see from here, we see that the magnetic field morphology is quite ordered. And especially we can see it seems to be also interestingly, we see kind of a flip between the for the main cloud filaments from the black box to the science box, which we can see it is a close to perpendicular on one side and almost parallel on the other side as well. And also we also spot quite some very strongest intensity spot along the 214 micron intensity map, which is known to have host protostellar objects. And also, interestingly, one of the sources, which is very mid-infrared bright, seems to be having hourglass morphology. So one of the key parameters to characterize the magnetic field properties in the infrared dark clouds is magnetic field strength map. So here we apply two equations here, which is essentially applying the DCF methods, assuming the equal partitions between magnetic and the turbulence energy, and that we can also see that by knowing the velocity dispersion, the dispersion in the angular of the polarization, and also the number density, then we can actually infer the plane of sky magnetic field here. And also there's also a correction here on the right panel, which is applied based on the method of Skalidis Tassis at 2021, which is by taking care into a different turbulence properties here. So in general, with this, we can see the plane of sky magnetic field strength is between 0.3 to 1.5 microgauss. And especially we can see also the very, very strong magnetic field strength towards the location where there's the dense core and really have active star formation activities. So one of the things that we can learn from this magnetic field strength map is to understand the relative importance of magnetic field in star formations. So here, one of the way to understand this is why the magnetic field strength density relation, or known as the B-row relations. So for cloud that form in star collapsing spherical cases, we see a B-row relation, which is a famous index of 2/3. And on the other hand, if we have magnetic field dominate cloud fragmentation, assuming the unity magnetic to gas pressure ratio, we actually find a more shallower index, which is roughly close to 0.5. So in this case, we can actually we have on the magnetic field strength map to do this. And here is the result we have. On the left, we actually plot the magnetic field strength against the column density. And on the right here, we show the magnetic field against the number density. In general, what we found is a much shallower index than the 2/3, which also seems to be consistent with the magnetic field dominated magnetic regulations, which is we have CC and index, which is 0.5 plus or minus 0.01. So another thing is also to study the relative importance of magnetic field is to use the mass-to-flux ratio. So mass-to-flux ratio is the way to dissect the raw gravity and magnetic field along the line of sight. So to do this, we actually need to scale the plane of sky to the line of sight by taking a factor of square root of 2. And in this case, from the plot here, we show that in general, on the larger outside of the cloud, we see a much more subcritical. In that case, this magnetic field is really much more important. And in the more in the cloud, which is the gravity has become more dominant, you can see the value is close to 1. So this equation, which is showing the mass-to-flux ratio, is normalized to the critical value. So in this case, if it is above 1, then in that case, we think that the gravity is much more dominated. And in this case, we see that towards the cloud become much more dominated by the gravity in some cases, which is well above 1 is where the star forming activities happen. And we think that in this case, we have seen the cases that gravity is really dominating. So and finally, one of the key things we want to assess the relative importance is really doing the energetics. So here we apply the virial theorem with surface term to really quantify the different contributions from the gravity, turbulence for thermal, and the magnetic energy here. So to here, we actually samples a large sample of dense core, which is based on Butler 10 and Cannon 2014, which is showing here on the right as the black circle. So we actually performed the dynamical analysis, including the surface term, and we found that in generally, we see that most of the dense core here, we have the kinetic plus the magnetic field energy seems to be stronger than the gravitational energy. So of course, another thing we also want to study is to look into the kinetic virial parameter, which is defined by this equation here, which is showing on this plot. We show all the virial parameter of this sample of dense core, and we find that in general, this is actually a little bit above 1. So in this case, that we think that it is really supported by turbulence plus magnetic field against the gravity. On the other hand, here we also probe another interesting parameter, which is also important, is the Alfvenic Mach number, which is essentially comparing the relative important magnetic field compared to turbulence. And in this case, we found that the value is about 0.2 to 0.27 for this sample of cores. So one thing we want to understand connecting the magnetic field properties and to really test different massive star formation models here. So one thing what we can do is we use the observational parameters and compare with the predictions from the model. So here we compare our observed parameter with the core accretion model predictions. So on here, we see there's the prediction with the velocity dispersion on the x-axis is actually prediction from the turbulence core model, which is assuming the core is at virial equilibrium and supported partially by the turbulence and magnetic field. And we can see that the observed velocity is much narrower than what we predicted on that. Another thing we also found that is actually the magnetic field is stronger than what is predicted by the turbulence core model. So in this case, we think that we need to account for a much stronger magnetic field support than what we previously think in massive star and star cluster formation. So another thing we also we have studied is to look into magnetic field orientations and the mass surface density. So here we use the histogram of relative orientations. So essentially, we study the relative orientation of the magnetic field and the intensity gradient. So we plot in here is the histogram of relative orientation on the left of the different using different density threshold, and also for the whole cloud on the right here. So in summary, we actually found quite a predominant relative orientation of the cloud, which seems to be perpendicular to the magnetic field orientations. And we actually characterize this by using a statistical test with the projected Reynolds statistic and the Cooper test as well to confirm such correlations. So another thing which is really interesting to study is the magnetic field orientation and some of the star formation properties, because this actually help us to really get some insight of how magnetic field might regulate different star formation properties. Especially on one of the things we look into here in this project is the outflow orientations. So here we use the outflow orientation sample study in Kong et al. 2019. And we actually plot the outflow orientations on the y-axis against the magnetic field orientations of those positions. And in general, it seems to found to be some bimodal orientations. And we plot this into a histogram, and we found to be apparent bimodal. However, we need to really test the significance with the statistical test. But with the projected Reynolds test and the Cooper test, we don't really see a strong indication of such correlations, which is comparing to the uniform distributions. So one of the reasons of that is because we have relatively still low number statistic here. So I think if we increase the number of statistics, then we can actually confirm if there's indeed such a unique bimodal distributions. So in such a case, I'm able to give a summary of this project. So we're actually able to study and characterize the magnetic field properties of a very massive infrared dark clouds G28.37. So we have characterized the magnetic field strength map by the refined DCF method. And from here, we actually get a relatively strong field strength from 0.3 to 1.5 milligauss throughout the cloud. And we characterize the relative importance of magnetic field by studying the B-rho relations and the mass-to-flux ratios. And in this result, we found that the magnetic field plays a dynamically important role in the cloud fragmentations. And we have performed a dynamical analysis to characterize also the magnetic field importance. And we found that there's quite a strong magnetic field support on the cloud as well. And this actually may allow us to rethink, or maybe we need to take this account for existing massive star formation models. And finally, we also study some of the morphological properties related to the star formations. In particular, we study the magnetic field orientation and outflow orientations, but we don't find a clear correlation between the magnetic field and the outflow orientations. So with this, I leave my summary slide here, and I would be ready to take questions. And thanks again for giving me the chance to share this exciting project.
Thank you very much for your presentation. Let me remind everyone to submit questions through the Q&A button at the bottom of the screen. And let me begin by asking you once again, to describe the significance of the plot in the lower left, which is the virial velocity dispersion versus what is in the vertical?
So the vertical is the observed velocity dispersion. And on the x-axis is the one that will be expected for the cases for a core predicted by the turbulence core accretion model, assuming the core is in the virial equilibrium supported mainly by the turbulence. And in this case, we found that what we observe is not as expected as the predictions. And also, we think that if the magnetic field, which is also we see actually stronger than what is predicted by the turbulent core accretion model. So what this means, or the significance of this, is actually mean that we need to account for a higher magnetic field support than what we previously think. And also we thought that the turbulence may have a much more significant role, but may not be that anymore as we expected.
Okay. And for the figure in the lower right, would you explain to me why you think this is not a significant correlation?
Well, one thing is we really want to compare to, for example, the Poisson error. In this case, for example, it's the square root of the count. And also from the really project Reynolds statistic here, we really cannot confirm this distribution is really really significantly compared to a uniform distribution, or if there's such a correlation. But one thing I do want to emphasize is, nonetheless, this is from a single cloud. So with such large amount of outflow within a single cloud is not that often. So of course, this is a little bit interesting, but we have to really confirm by really more number statistics to really beat down the possible noise and other source of bias from statistics, so before we can really say that there's such a correlation or not.
Okay. Let me remind people to submit questions through the Q&A button at the bottom of the screen. We do not have any open questions right now, but my understanding of your basic conclusion is that the magnetic field is dominant, is an important contributor to the dynamics of the core collapse?
I think the main take-home message is all these findings really, as I mentioned, that all these findings really indicate that magnetic field plays a crucial role in regulating massive star and star cluster formation, especially in the initial conditions, because the infrared dark cloud is an environment which really provide us a chance to look into the more earliest stages of massive star and star cluster formations.
Mm-hmm.
And these findings really tell us that this actually provide different evidence that magnetic field plays a dominant role, and this has to be taken in account when we consider different theoretical models and simulations.
Okay. Are there any other questions that come in? We have a few minutes left in the webinar. Since we have a few minutes left, Paul, is there anything you would like to elaborate on that you didn't get time to in your main presentation?
So this is actually a survey, and we are actually expanding this to other infrared dark clouds. So from here we will have other infrared dark cloud which is across different mass and size, scale, and also environment. So characterizing the magnetic field properties among all these different mass, size, and environment allow us to properly able to understand the relative importance of magnetic field in massive star and star cluster formation. So in such a case that we actually is an ongoing work on this, and stay tuned with more of these updates from the other infrared dark clouds as well.
Okay. We do have some questions, and one is, are the equations for the magnetic field strength map consistent? And the questioner is asking about the units.
So, okay, so I'm going back to the slides of the magnetic field strength. You mean this here?
Ah.
So if I understand the question correctly, so on the left here is the classical DCF method, and on the right is the refined DCF method, which is assuming a compressive turbulence cases. So in this case, the classical DCF methods normally is expected to overestimate the field strength especially in the high density regions. So that's why we're in Skalidis and Tassis 2021, they made such a corrections, and we applied such a cases on that, and we found indeed a range of magnetic field which is about 0.3 to 1.5 milligauss.
There's a clarification of that is there's a square root on the velocity dispersion, but only in one of the equations. Well, let's take that offline. That's a very—
Thank you, but I'm not quite sure on this.
Okay. Yes. You will get a link to the questionnaires email and be able to answer that. Here's another question. Magnetic field strengths inferred from dust polarization maps are subject to significant uncertainties. How significant do you think such uncertainties are for your conclusions?
So we have actually, I mean, I haven't shown in this slide, but we actually perform some method to really quantify the magnetic field strength. In general, it doesn't really changes the field strength a lot, but and also we don't think it has a huge impact on the conclusion that we have mentioned. So in summary, I would still say the result we still imply that magnetic field played quite an important role in this infrared dark cloud in particularly.
Mm-hmm. And I have a question about the general technique of inferring magnetic fields in this way. You really do not have a way to discriminate between foreground dust and the cloud, and possibly even some background dust. So is the assumption that the dominant polarized dust in this direction arises from this particular volume of space associated with the dark cloud?
Well, I mean, one thing of this, I mean, the thermal dust emission in this case, we actually taking the full line of sight. So of course, I don't particularly very know about this question, but one thing I would say is nowadays we have some background stars parallax to understand the different distance. So in this case, I think we can also help to disentangle this problem, I guess. But indeed, I
Yeah.
don't have a solid answer for this.
Okay. We have another question came in. Do you have any observational data suggesting an influence of binary formation or disruption due to magnetic fields?
We don't know because I think we haven't really studied this, especially on this infrared dark cloud. But I think this is something is interesting to look into.
Okay. Well, that ends the open questions. And so let me thank very much Paul Law from our Chetri Observatory, where he recently started a postdoc. Thank you very much for this most interesting presentation. As I said earlier, this has been recorded and will be available for viewing on the Green Bank Observatory website in a day or two. Please join us again in 2 weeks for the next in this series on April 24th, when Karen O'Neill will present A Galaxy Without Stars, ? We look forward to seeing you again. Thank you and goodbye.
Thanks. Bye.